Hi everyone. Thank you for coming to this talk named Why Oatmeal is Cheap, a Fundamental Theorem for Procedural Generators. My name is Younès Rabii. I'm an indie game developer, also a PhD student at Queen Mary University of London. I study automated game design, procedural generation, and this work that I'm going to present was done under the supervision of Dr. Michael Cook, a senior lecturer at King's College of London, an overall very cool and kind guy. We're going to speak about procedural content generation and the challenges that designers have to face when they work on them, and of a concept named Oatmeal that we're going to present today. So, first, procedural generation. What are generators? Basically, they are procedures that make something. Here we have a small program running live and designing labyrinths for hopefully 2D top-down games. But procedural generation has a practice. It's very, very old. It existed before computers. You can maybe think of cooking recipes as one example of procedural generation where you have a specific procedure to follow, and when you follow it, hopefully at the end you're supposed to have a good cookie. Or you could think of astrology divination as perhaps a form of procedural generation where, as an input, an astrologist will take your birth chart, the position of the stars and planets in the sky when you were born, and will generate, thanks to a specific personal procedure, a sort of fortune or divination for you. And there's all of that in multiple fields in arts and crafts. We have poems that are, for example, 1,000 billion poems by Raymond Queneau. It's a booklet where you can swap every verse. There's 14 verses. You can swap every verse for another version of them. And this idea is that you put one book, but you get 100 billion poems at the same time. There's the domains of mosaics or crochet, where by following some specific geometric patterns or even programs, in the case of crochet, at the end you get either a beautiful mosaic or a specific object made of wool. So the objects we get at the end of these procedures, in this field we call them artifacts. That's going to be important. We always call them artifacts. And of course, PCG, it might be one of the main reasons you know PCG is because it's widely used in games. And in this talk, I'm going to focus a little bit on games, because as I showed you before, PCG is like way, way bigger than just games. But yeah, PCG in games is also quite old. Basically, every game where there's like dice or cards or tiles, there's a form of PCG somewhere. So games like Mahjong have PCG. Sort of like generators have a procedure to generate an interesting Mahjong pile. Games, classics like Minesweeper, when you run them, each time they generate hopefully an interesting and balanced puzzle. It's fake, they're always too hard. And then you have games like roguelikes. The entire genre is built on this idea that you can generate interesting maps, interesting encounters that have the right level of challenge. And some character creators also have this concept of taking as an input the choices of a player and producing hopefully something that is hopefully aesthetically pleasing or interesting to the player. And yeah, of course, nowadays PCG is most often confused with machine learning, specifically not thanks to these huge generators that are Stable Diffusion, Midjourney, and the GPT family, GPT-1, 2, 3, ChatGPT, basically large language models and deep generating, image generating neural networks. At the core, PCG has a promise. There's a myth we say about PCG. This myth, it can be exemplified by this thing where, hey, you can have a very simple generator. Here's just like one line of code, but you can have infinite outputs. So many different labyrinths you can generate with this simple line of code. And this sort of like dichotomy between the shortness of generators and the vastness of the different outputs you can have created some myths that are present very strongly in the game industry. mainly people who don't have experience making generators would say that procedural generation can be used to lower budgets, that you can replace workers with some form of generators, and the workers will have more free time, it will be less expensive. And we even have many genres of games who use the size of what the generator can produce as a marketing point. There's the famous No Man's Sky, a game where you can explore 18 quintillion planets. What happens if we compare that to the actual experience of PCG designers? What do they say? Well, we have, for example, one of the designers for Spore, which tells us that there's a trade-off between the breadth of content you can make in one of these tools and the depth, the quality of that content. So it's not so simple as making infinitely many content. There's this idea of, are they interesting, are they good enough? More humoristically, we have famous PCG designers, Ortega 42, which tells us that thanks to PCG, I can produce twice the content in double the time. So there's this strong idea of, there's a myth of, yeah, we can cut costs, we can have infinitely interesting things, and there's no trade-off. We can have this with no issue. And of course, linked to these problems, there's the famous problem called the 10,000 balls of oatmeal problem, coined by Dr. Kate Compton, a researcher I admire, and I think is in the audience today. I'm not going to point at her unless she wants to. Okay, she's here. Hello, Kate. Nice to meet you. This idea is simple. Imagine we have like an oatmeal generator that says, hey, we can make so many different balls of oatmeal. They are all technically unique. They're so amazing. You can distinguish them from the other. You can have 18,000 billions of oatmeal bowls, and they all be going to be different. But the thing is, it's still oatmeal. They still taste exactly the same. So it's not enough for something to be different or to have a huge number of possibilities to actually be interesting. I'm going to nuance here because oatmeal is not necessarily bad per se. It just happens that it's often a complaint that some players of games who play games who promise something else. Like No Man's Sky players famously were a bit frustrated in the first edition of No Man's Sky at how repetitive those 18 quintillion planets were. But there's cases where oatmeal is perfectly fine, even desirable. We have, but in other industries, for instance, in graphical shaders and stuff, you want to be able to generate a huge ocean, and it's okay the ocean is not uniquely interesting in each kilometer of its surface. You just need to have a feeling of something overwhelming that is always the same but different at the same time. So yeah, I'm not going to go too deep here, but yeah, we will keep in mind that oatmeal can be desirable, but most often, in the case we're going to study, it's not going to be the case. So what are we going to do here? Today, in this talk, we're going to study PCG from, or generators specifically, from a fundamental mathematical level. This is a bit contrary to what has been done before. PCG has traditionally been explored, studied empirically. This means that we study the artifacts, we study the reaction of players to these artifacts, we study how human designers, various testimonies, how they work on it. And it makes sense. It makes sense because, as I showed you before, PCG existed before computers and is not just limited to software. But here, today, I'd like to, with you, if you're okay with this, I'd like to study generators from a mathematical point of view, in a specific formalism. But the goal here is not to go so abstract that we forget the links, that the roots of PCG, and that it's a practice. That human designers, even if theory can be beautiful and abstract, it's always more interesting when it relates to what the actual designers do. So each time I'm going to introduce a mathematical concept or a part of this theorem, I'm always going to link it at some point to the concepts that designers actually use, human designers, and or the challenges that we actually face. That's going to be my goal today, to build a bridge between fundamental theory and hopefully help us inform the challenges that designers have to face. So first of all, as in all mathematical books, we're going to start with some definitions. They're going to be light. If you're a huge math nerd, hello, I love you. But this work was a paper at first. So we're not going to be too deep in the proofs and demonstrations here, because it will take too much time, and also because yes, it's already accessible on the paper which project. I'm going to link it at the end of this talk. So I'm going to stay a bit surface level here. The first thing is to explain what we're going to study. There's many types of generators, and we're going to study a simple one that we call an ideal generator. We'll call it J, and an ideal generator G has these properties. First, it terminates. It always outputs something. It's not going to take an infinite amount of time before outputting something. Then, its inputs have always the same size, declared beforehand. So we have generators that can take 5 megabytes of information or 10 gigabytes, but each input will be exactly of the same length. And then there's a third property that we call injectivity. It just means that if you give it a different input, it gives you a different output. And in our case, inputs and outputs are always binary strings. And as you probably know, every data on a computer can be represented as a binary string. So that's a very handy format. Every data, even programs. Programs are also strings of binary numbers. That's going to be relevant later. And you might think that ideal generators are a bit limited, that they don't represent enough generators to be interesting. But the thing is, in a lot of cases, we can take a non-ideal generator and with a bit of magic, turn it into one that is ideal and make it so the theorem also works on them. We just took ideal generators because they're like way easier to study without having 3 pages of subtleties and nuances. So yeah, as I said before, we're going to introduce 3 mathematical concepts about the generators, 3 qualities. And the first quality of the generators we're going to study is the length of a generator, the length of its source code specifically. So here I wrote there's a simple, I think, planet generator. And maybe you would say that, yeah, the length, that's really relevant because I can always add more length without adding interesting information to this quantity. I can add 1,000 of white spaces, thousands of columns at the end of each line. But here we're going to always study programs that are written as shortly as possible, as succinct as possible. All the information is dense, is condensed. And yes, it's way less human readable, but here we're not going to study the affordance of programs. We're going to study the information they contain. So we'll always take the most compressed version of a program that is possible to have. And the way I relate it to a thing that designers actually have to think about, it's a concept I call uncoded knowledge. So uncoded knowledge represents the things that you have to do to just make your generator works. Before writing a cookie recipe, you need to know how to make cookies yourself. You need to have the skill and the knowledge and the practice that comes with it. And it's not enough to just wing it like my mother does. You need to actually give precise specifications. You can't just say, yeah, until it's done. You need to tell the computer until the temperature is at exactly this time and stuff. So you need to have knowledge to write a generator or have access to that knowledge. If you want to make a good map generator for a video game, you need to have access to level design knowledge. And after that, once you can actually write your generator, it comes with an upkeep. That knowledge has to be encoded. You need to be able to implement the procedure in code to specify it. And most of you, I think, in the audience have programmed before. You know how painful that is. But you have to test everything. You have to debug it. You have to sometimes document it if it's big enough to work with multiple people or across multiple timelines. You have to optimize it sometimes. It comes with a lot of costs in energy and time that are not just about writing the generator itself, but just like making it work consistently and work on it, of course. So the core point here is that it's costly. Uncoded knowledge represents the costs, the human costs of writing a generator. In in all the interesting relevance metrics: time, energy, coffee, all of those. The second one, the second quality we're going to study is called the possibility space, and specifically the size of a possibility space. So here I've taken an example that comes from a game that I'm making myself. So it's called Garden. Garden is a hopefully a cute 2D pixel art game, lo-fi, where you explore gardens made of generated flowers. Here there's like a sample from an early version of a generator, and we're going to suppose here that it's all the flowers that a generator can make. This set of all the possibilities for the outputs of a generator, this is what we call the possibility space. It contains all the things that the generator could possibly one day output, all the possible artifacts. And we're going to call P of J the number of these unique artifacts in G's possibility space. Here it's 100, and when you use a lowercase g, p, is going to be the log in base 2 of that number. Just because that's math, this is how it works. But also, intuitively, this is the number of bits you have to use to be able to label each of these artifacts in the possibility space. The way we relate it to actual things that we care as designers is the thing we would call scale, the scale of a generator. It's, in Borderlands 3, it will be the billions of possible guns you could have when playing the game. If you use a character maker like Picrew, the scale of a generator is the number of all the possible avatars and pictures you could have with that character maker. And sometimes scale exists but is a bit hidden. For instance, in Animal Crossing New Horizons, when you create a new game, they ask you to choose between 4 islands. But the thing is, this generator can make more than 4 islands. So if you start the game again, you will have different islands to choose from. So even if the game doesn't surface scale directly, scale always exists for players because they can always restart the game or explore the game in other ways. So scale represents the vastness of a possibility space. And the last one, which is the star of the show, the last quantity that we're going to speak about today, is named Kolmogorov complexity. Here's a simplified explanation. So if we take again the sprites from Garden, the game presented before, here's 2 different flowers or sprites that the generator could make. And the complexity of each of the sprites is the number of words you need to use to describe them. For instance, the check pattern on the top left, you can describe it quite easily in 4 words. Just say, yeah, alternate black and white pixels. The one right under, it's a bit more complex. You need to add a bit more knowledge to describe that artifact. You could say something like, yeah, it's a 9x9 red cross overlaid with a 3x3 white square in the center, and that will take you 13 words to explain. And if we take that to the extreme, if we, for example, take something that is almost totally randomized, sometimes you don't have much choice than just simply explaining how the data is bit by bit of information. There's no pattern, there's no smartness to have, you just have to explain it by saying, yeah, you just take a blue pixel, then a green pixel, then a yellow pixel, then a white pixel, etc., until the end. Because there's no much, because there's, it's, how to say that? It's not because there's not enough, there's no patterns in there, it's because there's too much pattern. It's way too complex to check all the different patterns that overlay to make this one. And we're going to give names to these quantities. So here's a sample again from Garden, and we're going to call K of A the complexity, the number of words or bits of information you have to use to explain a specific artifact. And we will always be mindful in this population of the one that is the most complex, that we call K star of J because it's only of G because it only depends on G specifically. And I made a typo here. K bar is not the same as K star. K bar is the average complexity, so it depends on all the other ones too. Yeah, just notations. Don't worry about it. How do we relate that to things that we experience as players or yeah, has players. It's a thing we call pattern density. So if here you have 4 black and white pictures, 4 white and black maps maybe for a video game, and I ranked them here by k complexity. And you can see that on the extreme of a scale, when you have something that has a very low Kolmogorov complexity, it's very repetitive. The patterns are very easy to spot because they can be described very succinctly. If you get more complex, it gets a bit harder and harder until there's a point where, for something that has a very high k complexity, there's too much pattern. Too much that you can't even notice them or register them. The artifact becomes noisy, and there's so much patterns that you can't see one. You just see a forest. You don't even see a tree. So that's the three quantities we're going to study, and we're going to use a plot, a graph to represent them. So on the x-axis here, I've put the scale of a generator G. On the y-axis, I've put uncoded knowledge, and I just plotted a generator G somewhere on that field. So there's a little ball, a little blue ball with a G under it. That's our generator, defined by its scale and encoded knowledge. And what we're going to do is that we're going to, little by little, each step of a theorem will remove space from that graph. Right now, the generator G could be anywhere on this graph. What we're going to show is that there's a strong relationship between all these things I presented before that makes it so G cannot be anywhere on this graph. There's huge constraints on how all these things are linked together. The theorem is made of 3 inequalities. Here's the first one. So here we say that k star of G is bigger than little p of G. So the highest complexity in the possibility space is bigger than the number of bits you have to use to label all the artifacts. Again, I promised that I won't go into too much details, but I'm going to still print the steps of a proof here because people will be able to watch them on YouTube and somehow work out how it works. But the core idea is very simple. It's just counting. If you have 2 to the n elements and you need to index them by a number, you will need to use at least n bits of data. That's it. That's the simple core of that, and then we express that with our specific variables. That's it. So what it means for our graph here is that there's this kind of no-go zone where J cannot go anymore. This no-go zone is defined, you can see on the x-axis, by the pattern density. When the pattern density is this high, J cannot go into that zone. This is what it means. And we're going to remove, again, more space on that graph. Inequality number 2, the size of J plus little p of J is bigger than the complexity of most complex artifacts. Again, just going to show the steps for YouTube, but here the argument is, again, simple. We just use the definition of complexity. Complexity is the length of the shortest program that can be used to define one artifact, and using J and giving the right inputs is a program that can output this artifact. So J plus the input is bigger than the complexity, and because our generator is ideal, there's as many inputs as outputs, so we can make a link between inputs and the number of things in the possibility space. That's it. If we go back to the graph, we removed another zone. So you have this zone on the bottom left. English is hard. Bottom left corner. That the generator G cannot be anymore. And last inequality. Our goal here, and I'm going to be a bit more specific because we might have, if I manage time right, we might have enough time to use that one to make something interesting. The goal here is to be able to put an upper bound on the length of G. So that is to say, we know that we have a generator that has these inputs and these outputs. But the thing is, how how do we know which size this generator has? How can we make sure that how can we estimate the smallest possible program that can output these artifacts? One way to do this is to build a program that can output those, and this program will always be either bigger or exactly the same as the most optimal program that can do this. So I used everyone's favorite language, Python, to write a template of a program that can output our artifacts here. So we have artifacts A0, A1, A2, up to AN, and each one of these artifacts have a specific program that can output them when you run them, and they are called P0, P1, P2. So basically, what you do is you make a list of all of these programs, kind of like a library. And if someone asks you, hey, can I have artifact number 3? You just say, yeah, sure. So artifact number 3, this is how it is described in the archives. Let me decompress it for you, and here you have it. So that's the formula in the question marks is going to be a bit complex, but with colors it's going to be a bit more simple. So you have the code in green, which is like the core of the templates. It's a constant. So what I call C1. You have in yellow the size of each of the smallest programs. So it's in yellow in Sigma, and then it's very it's very stupid, but we still have to account for it. There's a number of commas in the list, and the number of commas is 1 times the number of elements in there, -1, I think. And yeah, we have to account for it. So it's also a constant. It's in red. We can make some transformations on this formula. For example, like a very simple one would be, yeah, the size, the sum of all of these programs is just like the average times the size. Yeah, I'm not going to go too deep in here. I'm just going to show you what it ends up with. So this is the shape of a third zone that we can remove from the graph here. So what we have is strong constraints on the properties of G here. We know that G can be anywhere inside this black triangle, but can be outside. So it brings some tension between these variables, especially if, as a designer, you want to change some of these variables. Like if we want to, actually, let me show you why it's pixelated. It's because this graph is playable. So we have our little ball G here. On our generator can be anywhere on this graph when you plot scale and encoded knowledge. Remember, encoded knowledge is the cost of making the generator. So if J is here, it costs something. If J is here, it costs less. If we go up, it costs more. And if J is here, let's say we have like 100 artifacts. If we want to have more artifacts, we go to the right. If we want to have less, we go to the left. And we can't exactly go into these blue zones. Well, we can't go into these blue zones without changing pattern density. These are not like hard borders. They're more like walls that you can push. So if you want to make a generator that has a lot of scale, you can always do that. Push it. But it also means that you're increasing pattern density, right? So all of these things, it shows you the tension between all of them. How if you add more encoded knowledge, actual knowledge into the generator, you will also increase pattern density. If you decrease encoded knowledge, you decrease pattern density. If you increase scale, you increase pattern density, all of it. So these are all sort of like transformations you can make on a generator. And I'm going to show you how they relate to trade-offs that designers have to make when they design generators. Well, first example will be Minecraft's village updates. So we start with Minecraft with a version of Minecraft that doesn't have villages, and we want to add a new pattern in Minecraft. We want to add the possibility for worlds to feature villages. So we know that we need to add a new pattern, and we have a specific constraint, a technical constraint, which is that we can't really change scale. Because Minecraft, you might know that, but every Minecraft world has a specific ID, specific seed, which is written with 64 bits. always. So we can't change scale between versions. Minecraft before villages and after villages will have as many different worlds in that thing. But we still want to increase pattern density. So what are our choices here? I'm going to restart. So let's say this is Minecraft version 1, and we want to make it so Minecraft version 2 has a bigger pattern density. But we can't change scale. Scale is the x-axis, so we can't go left or right. We can only go up or down, and we want to increase pattern density. So our only choice is to increase, and to increase uncoded knowledge enough that we also increase pattern density at the same time. Now remember, uncoded knowledge is the costs that you put in there. So we know, thanks to this theorem, it's a bit obvious, but still, that Mojang didn't have any other choice when they made the village update to actually spend more time in their code to be smart about how they want to add their villages and to input more time, money, and coffee into the work. It doesn't have to always be the case. I'm going to again take my game to Garden as an example. So on the left, you have an example of what ideally I'd like to have, which is a small garden with a river and some generated flowers that make patterns in there. And initially, what I had was I worked on a generator, and my generator made 12 by 12 pixel sprites. As you can see, it's not so pretty, right? It's a bit ugly. It's a bit like super noisy and stuff. It doesn't fit the aesthetic of the garden. So I looked for a possible transformation on my generator to make it so what I would call here the pattern density. I want to make them less noisy, so decrease the pattern density to have something which is a bit more fitting to the aesthetic. So again, let's restart. So we start here in red, and we want to decrease pattern density. What are my options? I could decrease the scale, the encoded knowledge. So rework command generator and make it so make it less smart, basically. Or I could decrease scale. These are my options, and these two options come with trade-offs and consequences. If I decrease scale, I don't really have to change my generator. Actually, this is what I did. I just changed it so it still generates a 12 by 12 flower, but I only take the center 6 by 6 pixels. Or I could have done something else. I could have make my generator a bit less smart, feature less of my creativity and my aesthetic into the game. This is not the choice I made. So I want to decrease the scale on encoded knowledge at the cost of having less different possible flowers in my game. So I have less possible flowers, but they aesthetically are more pleasing and fit more what my game is about. Let me check time. I think I still have 5 minutes, that's it? Yeah, I think so. And now let's take the example that is sadly commonplace in the game industry. So we have games like Borderlands 3, No Man's Sky, where the size of possibility space is a marketing point. It's something that attracts people. It's in the trailers. It's in the bullet points they give to marketers. It doesn't always come from designers, but it's still something that exists. It's still a pressure on these games to be able to boast about the number of different possible things you can experiment in those games. And what are the constraints? Let's role play a bit as the game industry. So here we want to make a game that maximizes scale. We want to be able to say, hey, we have so many cool different planets to explore, or spaces, or galaxies and stuff, but we're the game industry. Our goal is also to minimize costs. So we need to increase scale, minimize costs. What does it mean? Increase scale, so we need to go somewhere to the right, and we can't go in diagonal, right? Because we don't have the right to go upwards, because going upwards will give us more, will cost us more uncoded knowledge, more resources. And our goal here is to minimize the number of times we go up. So we can go down left, right, down right, or just right. We can do this. Now I want to show you what happens to your artifacts when you do this. So I did like a little simulation of what happens. We have samples coming from generator G1 and generator G2, and look at what happens in the blue square to generator G2's artifacts. We increase scale. We don't increase encoded knowledge, increase, up to this point where, yes, we have increased scale a lot, but it was at the cost of increasing pattern density, and pushed to the extreme. This is what we end up with. You can see that G1 has artifacts that, okay, they're not so good, but they are distinct. They each have their own little personality. But G2, they all have unique artifacts, but they all the same to me. They're just noisy, they're just oatmeal, basically. So here what the theorem tells us is that some situations where you want to increase scale, but you can't increase encoded knowledge or the cost you put in the generator, are very favorable for the apparition of the oatmeal. This is what happened. This theorem is kind of a sort of maybe an equivalent to maybe the law of thermodynamics in physics, in the sense of they say something about the conservation of energy and the conservation of information. If you want to have truly relevant artifacts and increase the scale, you need to put more energy into the system. This is how it works. There is no really free meal, kind of. That's the idea. Or, as Max Kreminsky said, they called it the limited free breakfast theorem. You can have free meals, but you're going to eat oatmeal. That's basically it. I'd just like to check, can someone who's savvy with time tell me if I have more than 3 minutes or not? I have 3 minutes? Okay. All right. So I'm going to give you a sneak peek, but not go all the way to there. And if you want to know more, you can catch me at the break. The good thing about this theorem is that it's also good for approximations. Approximations are used in physics when you have very, very big systems to simplify equations and have ideas about this, basically the order of magnitude of some things. And here I'm going to ask you a question. How many different pictures can Stable Diffusion generate? Like, not exactly, but the magnitude of it. It's hard to know, right? How many different answers can ChatGPT generate? It's also hard to estimate. The next question is solved in the same way that you would solve the first two. How many different articles can Wikipedia generate? What do you think? You might think that Wikipedia is not a generator, but remember, in our formalism, it acts as exactly the same. You input something in the search bar, and Wikipedia's very smart algorithms, informed by the knowledge of many designers, will give you an article about St. Louis. So yeah, don't have a lot of time, but here we suppose that Wikipedia is a generator, and we fill all of the variables with what they actually represent. So the possibility space is the number of articles, K of j, the average compressed size of an article, and the size of j will be the size of Wikipedia's source code as compressed as possible. And this is the third inequation, because we are in a very, very big generator. Remember, this is Wikipedia, it's massive. The constants that I showed you before, the one for the template and one for the commas, they don't really matter here. So it's way simpler, the formula becomes way simpler as an approximation. And we can make an assumption here. The assumption, sadly, I would have more time. I would need more time to explain why I can do this. But the assumption here is that the articles of Wikipedia are different enough that it's simpler to just archive each one of them separately and give them like a library than to try to find one program that can generate 5 articles at the same time. Basically, they don't have enough shared knowledge to be able to predict one another efficiently. It's of course a bit false. Of course, Wikipedia articles would be able, because they're written in English at least, be able to have some common information, but that's the assumption we make. And if we make that assumption, we can make estimations about Wikipedia. If we take the Wikipedia's possibility space, multiply it by K of j, the average compressed size, we have an estimation for what is the order of magnitude of Wikipedia's archive. Here we have, with my numbers and estimations in March 2019, around 47 gigabytes. And the actual size of Wikipedia archives at the time was 16 gigabytes. The numbers are not exact. That's not what's important. What's important is the units. we are in gigabytes. We are in the right ballpark, basically. So we can do the same thing with stable diffusion, for instance. Take these variables, possibility space, average compressed size of a picture given by stable diffusion, and the size of stable diffusion source code compressed, of course. And we don't have the first one. We have the number 2 and 3. And we're going to estimate the first one. Again, same steps, estimations. Stable diffusion's version 1 takes about 10 gigabytes of space. It takes much more RAM, but on just raw disk space, it's 10 gigabytes. And the average size of a picture transmitted by stable diffusion is around 126 megabytes. It's a 2056 by 56 pictures. So that gives us an estimation of around, in the ballpark, of 8,000 different pictures for stable diffusion 1. And you might say, hey, but for sure we can make more than 8,000 different pictures. But in our case, the approximation we make is that each one of these pictures does not predict the other, meaning that you can take a picture, cut it to make other pictures, right? They should be distinct enough to do that. And because we know that stable diffusion can make more than 8,000 pictures, this means that stable diffusion for sure uses some of these pictures, some of these core 8,000s to make all the other ones. So we can say that there's around 8,000 truly unique pictures in stable diffusion, and that all the others are basically patchworks of these core 8,000s. Well, in the newer version of stable diffusion, that number is higher. I did the math for ChatGPT 2, but I don't have it on my slides, so catch me after the lunch break. Well, thank you. Thank you very much. It was a pleasure.